do one last example just to clue up this chapter. This last example is a little bit of a combination problem. It's probably a little more test-like than some of the other problems. One addition I'm going to make to our question is we're going to say, let's assume this diagram is to scale. Okay, first part of the problem says label the charges. Here's our two charges. Label them either positive or negative. So these red lines are the electric field lines. Can label that with an E. What we know about electric field lines is that they go into a negative, so this charge must be negative, and they go out of a positive. While we're thinking about our charges, if we count the number of electric field lines, we see that they're the same for each charge. That tells us that our charges have to have the same magnitude. Okay, all right, moving on. The equipotential lines are separated by 1,000 volts, so each of them are different by 1,000. Find the electric field at point A. So, how are we going to solve this problem? We do know that these two charges are equal, but we don't know the magnitude of the charges. This means we can't do E equals KQ over R squared because we don't know Q. So is there another thing we could do? Well, we do know the relationship between electric field and electric potential. Why don't we write that down and see if that helps give us an idea? So the relationship between electric field and electric potential is that electric field is the change in potential divided by the change in distance. This will give us the magnitude of the field. So if we can find a change in potential between any 2 points, if we can find the change in distance, we could divide those two things and find our electric field. To get our direction, we know that electric field goes from positive to negative, so the direction of the electric field at point A is to the right. Okay, so now we have an idea. So delta V over delta R will be V2 minus V1 divided by delta R, the distance between 2 points, 2 and 1. This means we should pick 2 points, points 1 and 2. If we want to find the electric field at point A, then the 2 points we pick should be on either side of A, and it should be symmetric. Because when we use a method like this, we find the electric field right in the middle of points 1 and 2. So I'm going to pick my 2 points right here and right here. So those will be my points 1 and 2. Label it 1 here, label it 2 here. Hopefully you can see that well enough. So delta R, I'm going to measure that with my ruler. V2 and V1, I'm going to need to know the potentials. How am I going to find the potentials? Well, if these two charges are equal magnitude and opposite sign, then I know that the net potential at any point will be the sum of the potential for this charge plus the sum of the potential for this, plus the potential for this charge. So let's ask, can I find the potential at point A? So VA would be V1 plus V2. That would be K times Q1 divided by R1. R1 is going to be our distance between here and here. I'm not going to draw that on my diagram because I just don't want it to get too full. But R1 is from point 1 to A plus K times Q2 divided by R2. R2 is from here to here. Due to the symmetry, R1 is equal to R2. We also know, because of the direction of the electric field lines and the number of the electric field lines, Q1 is negative of Q2. Okay, they're equal and opposite. This tells us that VA has to be 0. Okay, this is good. So my potential here along the green line that cuts through point A, that's 0 volts. Every line is separated by 1,000 volts. Our potential would be positive as we get closer to the positive charge. So this line is 1,000 volts. This one is 2,000. This one is 3,000. This one is 4,000. That one's 5,000. Likewise, over here on this side, as we go closer to the negative, we'll get negative potentials. Minus 1,000 volts, minus 2,000 volts, minus is 3,000 volts minus 4,000 volts. And let's throw in minus 5,000 volts as well. Okay, so now I've got my V1 and my V2s. So V2 is my potential along here, minus 1,000 volts. My V1 is my potential along here, minus 1,000 volts, divided by delta R. And if I want to find the magnitude of the field, I'll do the magnitude of the potential divided by the magnitude of the field. To find my distance, I'm just going to put my R on my diagram, and I'm going to find my distance. That distance, it's a little bit hard to see perfectly. I think it's about 13 millimeters. So it goes a little past the 1, about as far as the 13. So we'll say measure with ruler. "13 millimeters is going to be 13 times 10 to the minus 3 meters. And our electric field then turns out to be have a magnitude of 1.54 times 10 to the 5 volts per meter. The direction is to the right. We'll call that the plus I direction. So we'll call that I hat. So there's our electric field at point A. Next, what is the work done by the field on an electron as it moves from point B to point C? So we'll release an electron here. It's going to move around. It'll come to point C. And what will be the work done on it? So let's call that one A. So this is A, this is B, and this is C. B. What is the work done on an electron by the electric field? We know that work is the negative of the change in electric potential energy. So that's going to be negative of the charge times the electric potential. That's the charge of the electron. Charge of an electron is negative of the fundamental charge. Negative times negative gives us a positive. Delta V is our final potential. It stops at point C. So that's my potential at C. Subtract my initial potential. It started at B. So that's point B. Okay, now I can just pop my numbers in. So my work done is positive of the fundamental charge, 1.6 times 10 to the minus 19 coulombs. VC, I wrote on my diagram that was minus 5,000 volts. Subtract VB, my diagram says that that's 3,000 volts. That gives us negative 1.28 times 10 to the minus 15 joules. Because the work done by the electric field is negative, it means it didn't move this way by itself. Some external force had to push it to get to point C. Okay, part C. If a proton is released at point B, what will be its speed as it reaches point C? So we know we're going to release it here. It's going to stop here. Find the speed. So this is not a case where we can use kinematics because the forces and acceleration are all changing. If we can't use kinematics, we'll use conservation of energy. So in our conservation of energy, our final mechanical energy is our initial mechanical energy. We had the work done by non-conservative forces. There's no friction, so that work done is 0. My final point is point C, and my initial point is point B. It moves from B to C. So my mechanical energy at C equals my mechanical energy at B because there's no losses due to friction. My mechanical at C is the kinetic at C plus the potential at C. That's equal to the kinetic at B plus the potential at B. Let's see what I can fill in for all of these things. So my kinetic energy at point C is 1/2 times the mass of a proton times the speed at C squared, and keeping in mind that V at C is the thing I'm trying to find. My electric potential energy at C, UEC, is my charge on my proton, that's plus the fundamental charge, times my potential at C. My kinetic energy at B is 1/2 the mass of the proton times the speed at B squared, but it was released from rest, so that's just 0. And my electric potential energy at point C, point B, sorry, my electric potential energy at B is the charge of the proton times the potential at B. Okay, I've got all of my things in here. So 1/2 times the mass of the proton times VC squared plus E times VC equals 0 plus E times VB. I can do some rearranging here to see that my speed at C is 2 times the fundamental charge times VB minus VC divided by the mass of the proton. Take the square root. Some numbers we know here. Mass of a proton is 1.67 times 10 to the minus 27 kilograms. Fundamental charge is 1.6 times 10 to the minus 19 coulombs. VC equals minus 5,000 volts, and VB equals 3,000 volts. Put all this through the calculator and we get 1.6